From Local to Global, a graph RAG approach to query-focused summarization. Darren Edge 1, Ha-Trin Newman Cheng, Joshua Bradley, Alex Chow, Apurva Modi, Stephen Truitt, Jonathan Larson. Abstract. The use of retrieval-augmented generation to retrieve relevant information from an external knowledge source enables large language models, LLMs, to answer questions over private and/or previously unseen document collections. However, RAG fails on global questions directed at an entire text corpus, such as what are the main themes in the dataset, since this is inherently a query-focused summarization (QFS) task, rather than an explicit retrieval task. Prior QFS methods, meanwhile, fail to scale to the quantities of text indexed by typical RAG systems. To combine the strengths of these contrasting methods, we propose a graph RAG approach to question answering over private text corpora that scales with both the generality of user questions and the quantity of source text to be indexed. Our approach uses an LLM to build a graph-based text index in 2 stages. First, to derive an entity knowledge graph from the source documents, then to pre-generate community summaries for all groups of closely related entities. Given a question, each community summary is used to generate a partial response, before all partial responses are again summarized in a final response to the user. For a class of global sense-making questions over datasets in the 1 million token range, we show that graph RAG leads to substantial improvements over a naive RAG baseline for both the comprehensiveness and diversity of generated answers. An open-source, Python-based implementation of both global and local graph RAG approaches is forthcoming at https:/aka.ms/graphrag. Introduction. Human endeavors across a range of domains rely on our ability to read and reason about large collections of documents, often reaching conclusions that go beyond anything stated in the source texts themselves. With the emergence of large language models, LLMs, we are already witnessing attempts to automate human-like sense-making in complex domains like scientific discovery and intelligence analysis, where sense-making is defined as preprint, under review. Figure 1. Graph RAG pipeline using an LLM-derived graph index of source document text. This index spans nodes, e.g. entities, edges, e.g. relationships, and covariates, e.g. claims, that have been detected, extracted, and summarized by LLM prompts tailored to the domain of the dataset. Community detection is used to partition the graph index into groups of elements, nodes, edges, covariates, that the LLM can summarize in parallel at both indexing time and query time. The global answer to a given query is produced using a final round of query-focused summarization over all community summaries reporting relevance to that query. A motivated, continuous effort to understand connections, which can be among people, places, and events, in order to anticipate their trajectories and act effectively. Supporting human-led sense-making over entire text corpora, however, needs a way for people to both apply and refine their mental model of the data by asking questions of a global nature. Retrieval-augmented generation is an established approach to answering user questions over entire datasets, but it is designed for situations where these answers are contained locally within regions of text whose retrieval provides sufficient grounding for the generation task. Instead, a more appropriate task framing is query-focused summarization, and in particular, query-focused abstractive summarization that generates natural language summaries and not just concatenated excerpts. In recent years, however, such distinctions between summarization tasks that are abstractive versus extractive, generic versus query-focused, and single document versus multi-document have become less relevant. While early applications of the transformer architecture showed substantial improvements on the state-of-the-art for all such summarization tasks, these tasks are now trivialized by modern LLMs, including the GPT, Llama, and Gemini series, all of which can use in-context learning to summarize any content provided in their context window. The challenge remains, however, for query-focused abstractive summarization over an entire corpus. Such volumes of text can greatly exceed the limits of LLM context windows, and the expansion of such windows may not be enough, given that information can be lost in the middle of longer contexts. In addition, although the direct retrieval of text chunks in nav-RAG is likely inadequate for QFS tasks, it is possible that an alternative form of pre-indexing could support a new RAG approach specifically targeting global summarization. In this paper, we present a graph-RAG approach based on global summarization of an LLM-derived knowledge graph, Figure 1. In contrast with related work that exploits the structured retrieval and traversal affordances of graph indexes subsection 4.2, we focus on a previously unexplored quality of graphs in this context, their inherent modularity and the ability of community detection algorithms to partition graphs into modular communities of closely related nodes. LLM-generated summaries of these community descriptions provide complete coverage of the underlying graph index and the input documents it represents. Query-focused summarization of an entire corpus is then made possible using a MapReduce approach. First, using each community summary to answer the query independently and in parallel, then summarizing all relevant partial answers into a final global answer. Figure 2. How the entity references detected in the HotPotQA dataset varies with chunk size and gleanings for our generic entity extraction prompt with GPT-4 Turbo. To evaluate this approach, we used an LLM to generate a diverse set of activity-centered sense-making questions from short descriptions of 2 representative real-world datasets, containing podcast transcripts and news articles respectively. For the target qualities of comprehensiveness, diversity, and empowerment defined in subsection 3.4 that develop understanding of broad issues and themes, we both explore the impact of varying the hierarchical level of community summaries used to answer queries, as well as compare to naive RAG and global MapReduce summarization of source texts. We show that all global approaches outperform naive RAG on comprehensiveness and diversity, and that graph RAG with intermediate and low-level community summaries shows favorable performance over source text summarization on these same metrics at lower token costs. 2. Graph RAG approach and pipeline. We now unpack the high-level data flow of the graph RAG approach, Figure 1, and pipeline, describing key design parameters, techniques, and implementation details for each step. 2.1 Source documents text chunks. A fundamental design decision is the granularity with which input texts extracted from source documents should be split into text chunks for processing. In the following step, each of these chunks will be passed to a set of LLM prompts designed to extract the various elements of a graph index. Longer text chunks require fewer LLM calls for such extraction, but suffer from the recall degradation of longer LLM context windows. This behavior can be observed in Figure 2 in the case of a single extraction round, i.e. with 0 gleanings. On a sample dataset, using a chunk size of 600 token extracted almost twice as many entity references as when using a chunk size of 2400. While more references are generally better, any extraction process needs to balance recall and precision for the target activity. 2.2 Text chunks, element instances. The baseline requirement for this step is to identify and extract instances of graph nodes and edges from each chunk of source text. We do this using a multi-part LLM prompt that first identifies all entities in the text, including their name, type, and description, before identifying all relationships between clearly related entities, including the source and target entities and a description of their relationship. Both kinds of element instance are output in a single list of delimited tuples. The primary opportunity to tailor this prompt to the domain of the document corpus lies in the choice of few-shot examples provided to the LLM for in-context learning. For example, while our default prompt extracting the broad class of named entities like people, places, and organizations is generally applicable, domains with specialized knowledge, e.g. science, medicine, law, will benefit from few-shot examples specialized to those domains. We also support a secondary extraction prompt for any additional covariates we would like to associate with the extracted node instances. Our default covariate prompt aims to extract claims linked to detected entities, including the subject, object, type, description, source text span, and start and end dates. To balance the needs of efficiency and quality, we use multiple rounds of gleanings, up to a specified maximum, to encourage the LLM to detect any additional entities it may have missed on prior extraction rounds. This is a multi-stage process in which we first ask the LLM to assess whether all entities were extracted using a logit bias of 100 to force a yes-no decision. If the LLM responds that entities were missed, then a continuation indicating that many entities were missed in the last extraction encourages the LLM to glean these missing entities. This approach allows us to use larger chunk sizes without a drop in quality, Figure 2. Or the forced introduction of noise. 2-3 element instances, element summaries. The use of an LLM to extract descriptions of entities, relationships, and claims represented in source texts is already a form of abstractive summarization, relying on the LLM to create independently meaningful summaries of concepts that may be implied but not stated by the text itself, e.g., the presence of implied relationships. To convert all such instance-level summaries into single blocks of descriptive text for each graph element, i.e., entity node, relationship edge, and claim covariate, requires a further round of LLM summarization over matching groups of instances. A potential concern at this stage is that the LLM may not consistently extract references to the same entity in the same text format, resulting in duplicate entity elements and thus duplicate nodes in the entity graph. However, since all closely related communities of entities will be detected and summarized in the following step, and given that LLMs can understand the common entity behind multiple name variations, our overall approach is resilient to such variations, provided there is sufficient connectivity from all variations to a shared set of closely related entities. Overall, our use of rich descriptive text for homogeneous nodes in a potentially noisy graph structure is aligned with both the capabilities of LLMs and the needs of global query-focused summarization. These qualities also differentiate our graph index from typical knowledge graphs, which rely on concise and consistent knowledge triples, subject, predicate, object, for downstream reasoning tasks. 2.4 Element Summaries. Graph Communities. The index created in the previous step can be modeled as an homogeneous, undirected weighted graph, in which entity nodes are connected by relationship edges, with edge weights representing the normalized counts of detected relationship instances. Given such a graph, a variety of community detection algorithms may be used to partition the graph into communities of nodes with stronger connections to one another than to the other nodes in the graph. In our pipeline, we use Leiden on account of its ability to recover hierarchical community structure of large-scale graphs efficiently, Figure 3. Each level of this hierarchy provides a community partition that covers the nodes of the graph in a mutually exclusive, collective exhaustive way, enabling divide-and-conquer global summarization. 2.5 Graph Communities, Community Summaries. The next step is to create report-like summaries of each community in the Leiden hierarchy, using a method designed to scale to very large datasets. These summaries are independently useful in their own right as a way to understand the global structure and semantics of the dataset, and may themselves be used to make sense of a corpus in the absence of a question. For example, a user may scan through community summaries at one level, looking for general themes of interest, then follow links to the reports at the lower level that provide more details for each of the subtopics. Here, however, we focus on their utility as part of a graph-based index used for answering global queries. Community summaries are generated in the following way. Figure 3. Graph communities detected using the Leiden algorithm over the multi-hop RAG dataset as indexed. Circles represent entity nodes with size proportional to their degree. Node layout was performed via OpenORD and Force Atlas 2. Node colors represent entity communities shown at two levels of hierarchical clustering, A, level 0, corresponding to the hierarchical partition with maximum modularity, and B, level 1, which reveals internal structure within these root-level communities. Leaf-level communities. The element summaries of a leaf-level community, nodes, edges, covariates, are prioritized and then iteratively added to the LLM context window until the token limit is reached. The prioritization is as follows. For each community edge in decreasing order of combined source and target node degree, i.e. overall prominence, add descriptions of the source node, target node, linked covariates, and the edge itself. Higher-level communities. If all element summaries fit within the token limit of the context window, proceed as for leaf-level communities and summarize all element summaries within the community. Otherwise, rank subcommunities in decreasing order of element summary tokens and iteratively substitute subcommunity summaries shorter for their associated element summaries longer until fit within the context window is achieved. 2.6 Community Summaries. Community Answers, Global Answer. Given a user query, the community summaries generated in the previous step can be used to generate a final answer in a multi-stage process. The hierarchical nature of the community structure also means that questions can be answered using the community summaries from different levels, raising the question of whether a particular level in the hierarchical community structure offers the best balance of summary detail and scope for general sense-making questions evaluated in Section 3. For a given community level, the global answer to any user query is generated as follows. Prepare community summaries. Community summaries are randomly shuffled and divided into chunks of pre-specified token size. This ensures relevant information is distributed across chunks rather than concentrated and potentially lost in a single context window. Map community answers. Generate intermediate answers in parallel, one for each chunk. The LLM is also asked to generate a score between 0 and 100, indicating how helpful the generated answer is in answering the target question. Answers with score 0 are filtered out, reduced to global answer. Intermediate community answers are sorted in descending order of helpfulness score and iteratively added into a new context window until the token limit is reached. This final context is used to generate the global answer returned to the user. Table 1. Examples of potential users, tasks, and questions generated by the LLM based on short descriptions of the target datasets. Questions target global understanding rather than specific details. 3. Evaluation. 3.1 datasets. We selected 2 datasets in the 1 million token range, each equivalent to about 10 novels of text and representative of the kind of corpora that users may encounter in their real-world activities. Podcast transcripts. Compiled transcripts of podcast conversations between Kevin Scott, Microsoft CTO, and other technology leaders. Size, 669 x 600 token text chunks, with 100 token overlaps between chunks, 1 million tokens. News articles. Benchmark dataset comprising news articles published from September 2013 to December 2023 in a range of categories, including entertainment, business, sports, technology, health, and science. Size, 397 x 600 token text chunks, with 100 token overlaps between chunks, 1.7 million tokens. 3.2 Queries. Many benchmark datasets for open domain question answering exist, including HotPotQA, Multi-Hop RAG, and MT-Bench. However, the associated question sets target explicit fact retrieval rather than summarization for the purpose of data sense making, i.e., the process through which people inspect, engage with, and contextualize data within the broader scope of real-world activities. Similarly, methods for extracting latent summarization queries from source texts also exist, but such extracted questions can target details that betray prior knowledge of the texts. To evaluate the effectiveness of RAG systems for more global sense-making tasks, we need questions that convey only a high-level understanding of dataset contents and not the details of specific texts. We used an activity-centered approach to automate the generation of such questions. Given a short description of a dataset, we asked the LLM to identify n potential users and n tasks per user. Then, for each user-task combination, we asked the LLM to generate n questions that require understanding of the entire corpus. For our evaluation, a value of n equals 5 resulted in 125 test questions per dataset. Table 1 shows example questions for each of the 2 evaluation datasets. 3.3 Conditions. We compare 6 different conditions in our analysis, including graph RAG using 4 levels of graph communities, C0, C1, C2, C3, a text summarization method applying our MapReduce approach directly to source texts, TS, and a nav semantic search RAG approach, SS, CO, uses root-level community summaries, fewest in number, to answer user queries. C1 uses high-level community summaries to answer queries. These are subcommunities of C0 if present, otherwise C0 communities projected down. C2 uses intermediate-level community summaries to answer queries. These are subcommunities of C1 if present, otherwise C1 communities projected down. C3 uses low-level community summaries, greatest in number, to answer queries. These are subcommunities of C2 if present, otherwise C2 communities projected down. TS. The same method as in subsection 2.6, except source texts, rather than community summaries, are shuffled and chunked for the map-reduced summarization stages. SS. An implementation of na-avrag, in which text chunks are retrieved and added to the available context window until the specified token limit is reached. The size of the context window and the prompts used for answer generation are the same across all 6 conditions, except for minor modifications to reference styles to match the types of context information used. Conditions only differ in how the contents of the context window are created. The graph index supporting conditions C0-C3 was created using our generic prompts for entity and relationship extraction only, with entity types and few-shot examples tailored to the domain of the data. The graph indexing process used a context window size of 600 tokens with 1 gleaning for the podcast dataset and 0 gleanings for the news dataset. 3.4 Metrics. LLMs have been shown to be good evaluators of natural language generation, achieving state-of-the-art or competitive results compared against human judgments. While this approach can generate reference-based metrics when gold standard answers are known, it is also capable of measuring the qualities of generated texts, e.g., fluency, in a reference-free style, as well as in head-to-head comparison of competing outputs. LLMs have also shown promise at evaluating the performance of conventional RAG systems, automatically evaluating qualities like context relevance, faithfulness, and answer relevance. Given the multi-stage nature of our graph RAG mechanism, the multiple conditions we wanted to compare, and the lack of gold standard answers to our activity-based sense-making questions, we decided to adopt a head-to-head comparison approach using an LLM evaluator. We selected 3 target metrics capturing qualities that are desirable for sense-making activities, as well as a control metric, directness, used as an indicator of validity. Since directness is effectively in opposition to comprehensiveness and diversity, we would not expect any method to win across all 4 metrics. Our head-to-head measures computed using an LLM evaluator are as follows. Comprehensiveness. How much detail does the answer provide to cover all aspects and details of the question? Diversity. How varied and rich is the answer in providing different perspectives and insights on the question? Empowerment. How well does the answer help the reader understand and make informed judgments about the topic? Directness. How specifically and clearly does the answer address the question? Or our evaluation, the LLM is provided with the question, target metric, and a pair of answers, and asked to assess which answer is better according to the metric as well as why. It returns the winner if one exists, otherwise a tie if they are fundamentally similar and the differences are negligible. To account for the stochasticity of LLMs, we run each comparison 5 times and use mean scores. Table 2 shows an example of LLM-generated assessment. Question. Which public figures are repeatedly mentioned across various entertainment articles? Graph RAG. Overview of prominent public figures in entertainment. The entertainment industry is vast and diverse, encompassing film, television, music, sports, and digital media. Certain public figures stand out due to their significant contributions and influence across these sectors. The following summary highlights key individuals who are repeatedly mentioned in various entertainment articles, reflecting their impact and presence within the industry. Actors and directors, public figures in controversy, musicians and executives, athletes and coaches, influencers and entrepreneurs. The repeated mention of these figures in entertainment articles signifies their ongoing relevance and the public's interest in their work. Their influence spans across various aspects of entertainment, from shaping cultural narratives in film and television to driving trends in music and digital media. These individuals not only contribute to their respective fields, but also influence the broader cultural landscape, often becoming central figures in social discussions and public discourse. NavRag. Public figures who are repeatedly mentioned across various entertainment articles include Taylor Swift, Travis Kelce, Britney Spears, and Justin Timberlake. These individuals have been highlighted for various reasons, ranging from their professional achievements to their personal lives. Taylor Swift, Travis Kelce, Britney Spears, Justin Timberlake. These figures are frequently covered due to their high-profile status and the public's interest in their careers and personal lives. Their activities, whether in music, sports, or personal relationships, have significant cultural and economic impacts, as evidenced by the media coverage and public reactions. LLM Decision Comprehensiveness. Winner 1, Graph RAG. Answer 1 is better because it provides a more comprehensive and detailed list of public figures from a wider range of entertainment sectors, including film, television, music, sports, gaming, and digital media. It also includes specific examples of their contributions and the impact they have on their respective fields, as well as mentions of controversies and their implications. Answer 2, while detailed in its coverage of a few individuals, is limited to a smaller number of public figures and focuses primarily on their personal lives and relationships, rather than a broad spectrum of their professional influence across the entertainment industry. D. Diversity. Winner equals 1, Graph RAG. Answer 1 is better because it provides a more varied and rich response by covering a wide range of public figures from different sectors of the entertainment industry, including film, television, music, sports, gaming, and digital media. It offers insights into the contributions and influence of these figures, as well as controversies and their impact on public discourse. The answer also cites specific data sources for each mentioned figure, indicating a diverse range of evidence to support the claims. In contrast, Answer 2 focuses on a smaller group of public figures, primarily from the music industry and sports, and relies heavily on a single source for data, which makes it less diverse in perspectives and insights. Empowerment. Winner 1, Graph RAG. Answer 1 is better because it provides a comprehensive and structured overview of public figures across various sectors of the entertainment industry, including film, television, music, sports, and digital media. It lists multiple individuals, providing specific examples of their contributions and the context in which they are mentioned in entertainment articles, along with references to data reports for each claim. This approach helps the reader understand the breadth of the topic and make informed judgments without being misled. In contrast, Answer 2 focuses on a smaller group of public figures and primarily discusses their personal lives and relationships, which may not provide as broad an understanding of the topic. While Answer 2 also cites sources, it does not match the depth and variety of Answer 1. Directness. Winner equals 2, NAG. Answer 2 is better because it directly lists specific public figures who are repeatedly mentioned across various entertainment articles, such as Taylor Swift, Travis Kelce, Britney Spears, and Justin Timberlake, and provides concise explanations for their frequent mentions. Answer 1, while comprehensive, includes a lot of detailed information about various figures in different sectors of entertainment, which, while informative, does not directly answer the question with the same level of conciseness and specificity as Answer 2. Table 2, example question for the news article dataset, with generated answers from Graph RAG, C2, and Nav RAG, as well as LLM-generated assessments. Figure 4, head-to-head win rate percentages of row condition over column condition across two datasets, 4 metrics and 125 questions per comparison, each repeated 5 times and averaged. The overall winner per dataset and metric is shown in bold. Self-win rates were not computed but are shown as the expected 50% for reference. All Graph RAG conditions outperformed naive RAG on comprehensiveness and diversity. Conditions C1, C3 also showed slight improvements in answer comprehensiveness and diversity over TS, global text summarization without a graph index. 3.5 configuration. The effect of context window size on any particular task is unclear, especially for models like GPT-4 Turbo with a large context size of 128K tokens. Given the potential for information to be lost in the middle of longer contexts, we wanted to explore the effects of varying the context window size for our combinations of datasets, questions, and metrics. In particular, our goal was to determine the optimum context size for our baseline condition SS, and then use this uniformly for all query time LLM use. To that end, we tested 4 context window sizes, 8K, 16K, 32K, and 64K. Surprisingly, the smallest context window size tested, 8K, was universally better for all comparisons on comprehensiveness, average win rate of 58.1%, while performing comparably with larger context sizes on diversity, average win rate equal 52.4%, and empowerment, average win rate equal 51.3%. Given our preference for more comprehensive and diverse answers, we therefore used a fixed context window size of 8K tokens for the final evaluation. 3.6 Results. The indexing process resulted in a graph consisting of 8,564 nodes and 2,691 edges for the podcast dataset, and a larger graph of 15,754 nodes and 19,520 edges for the news dataset. Table 3 shows the number of community summaries at different levels of each graph community hierarchy. Global approaches versus naive RAG. As shown in Figure 4, global approaches consistently outperform the naive RAG SS approach in both comprehensiveness and diversity metrics across datasets. Specifically, global approaches achieved comprehensiveness win rates between 72 to 83% for podcast transcripts and 72 to 80% for news articles, while diversity win rates range from 75 to 82% and 62 to 71% respectively. Our use of directness as a validity test also achieved the expected results, i.e. that naive RAG produces the most direct responses across all comparisons. Table 3. Number of context units, community summaries for C0, C3, and text chunks for TS, corresponding token counts, and percentage of the maximum token count. MapReduce summarization of source text is the most resource-intensive approach, requiring the highest number of context tokens. Root-level community summaries, 0, require dramatically fewer tokens per query, 9x 43x. Community summaries versus source texts. When comparing community summaries to source texts using GraphRag, community summaries generally provided a small but consistent improvement in answer comprehensiveness and diversity, except for root-level summaries. Intermediate-level summaries in the podcast dataset and low-level community summaries in the news dataset achieved comprehensiveness win rates of 57% and 64%, respectively. Diversity win rates were 57% for podcast intermediate-level summaries and 60% for news low-level community summaries. Table 3 also illustrates the scalability advantages of GraphRag compared to source text summarization. For low-level community summaries, C3, GraphRag required 26 to 33% fewer context tokens, while for root-level community summaries, C0, it required over 97% fewer tokens. For a modest drop in performance compared with other global methods, root-level GraphRag offers a highly efficient method for the iterative question answering that characterizes sense-making activity while retaining advantages in comprehensiveness, 72% win rate, and diversity, 62% win rate, over NavRag. Empowerment. Empowerment comparisons showed mixed results for both global approaches versus NavRag, SS, and GraphRag approaches versus source text summarization, TS. Ad hoc LLM use to analyze LLM reasoning for this measure indicated that the ability to provide specific examples, quotes, and citations was judged to be key to helping users reach an informed understanding. Tuning element extraction prompts may help to retain more of these details in the GraphRag index. 4 related work. 4.1 RAG approaches and systems. When using LLMs, RAG involves first retrieving relevant information from external data sources, then adding this information to the context window of the LLM along with the original query. NaRag approaches do this by converting documents to text, splitting text into chunks, and embedding these chunks into a vector space in which similar positions represent similar semantics. Queries are then embedded into the same vector space, with the text chunks of the nearest k-vectors used as context. More advanced variations exist, but all solve the problem of what to do when an external dataset of interest exceeds the LLM's context window. Advanced RAG systems include pre-retrieval, retrieval, post-retrieval strategies designed to overcome the drawbacks of NaRag, while modular RAG systems include patterns for iterative and dynamic cycles of interleaved retrieval and generation. Our implementation of GraphRag incorporates multiple concepts related to other systems. For example, our community summaries are a kind of self-memory for generation-augmented retrieval that facilitates future generation cycles, while our parallel generation of community answers from these summaries is a kind of iterative or federated retrieval generation strategy. Other systems have also combined these concepts for multi-document summarization and multi-hop question answering. Our use of a hierarchical index and summarization also bears resemblance to further approaches, such as generating a hierarchical index of text chunks by clustering the vectors of text embeddings or generating a tree of clarifications to answer multiple interpretations of ambiguous questions. However, none of these iterative or hierarchical approaches use the kind of self-generated graph index that enables GraphRag. 4.2 Graphs and LLMs. Use of graphs in connection with LLMs and RAG is a developing research area, with multiple directions already established. These include using LLMs for knowledge graph creation and completion, as well as for the extraction of causal graphs from source texts. They also include forms of advanced RAG, where the index is a knowledge graph, where subsets of the graph structure or derived graph metrics are the objects of inquiry, where narrative outputs are strongly grounded in the facts of retrieved subgraphs, where retrieved event plot subgraphs are serialized using narrative templates, and where the system supports both creation and traversal of text relationship graphs for multi-hop question answering. In terms of open-source software, a variety of graph databases are supported by both the LangChain and Llama Index libraries, while a more general class of graph-based RAG applications is also emerging, including systems that can create and reason over knowledge graphs in both Neo4j and Nebula graph formats. Unlike our GraphRag approach, however, none of these systems use the natural modularity of graphs to partition data for global summarization. Discussion. Limitations of evaluation approach. Our evaluation to date has only examined a certain class of sense-making questions for 2 corpora in the region of 1 million tokens. More work is needed to understand how performance varies across different ranges of question types, data types, and dataset sizes, as well as to validate our sense-making questions and target metrics with end users. Comparison of fabrication rates, e.g., using approaches like self-check GPT, would also improve on the current analysis. Trade-offs of building a graph index. We consistently observed GraphRag achieve the best head-to-head results against other methods, but in many cases the graph-free approach to global summarization of source texts performed competitively. The real-world decision about whether to invest in building a graph index depends on multiple factors, including the compute budget, expected number of lifetime queries per dataset, and value obtained from other aspects of the graph index, including the generic community summaries and the use of other graph-related RAG approaches. Future work. The graph index, rich text annotations, and hierarchical community structure supporting the current GraphRag approach offer many possibilities for refinement and adaptation. This includes RAG approaches that operate in a more local manner via embedding-based matching of user queries and graph annotations, as well as the possibility of hybrid RAG schemes that combine embedding-based matching against community reports before employing our MapReduce summarization mechanisms. This roll-up operation could also be extended across more levels of the community hierarchy, as well as implemented as a more exploratory drill-down mechanism that follows the information sent contained in higher-level community summaries. 6. Conclusion. We have presented a global approach to GraphRag, combining knowledge graph generation, retrieval-augmented generation RAG, and query-focused summarization QFS to support human sense-making over entire text corpora. Initial evaluations show substantial improvements over a NavRag baseline for both the comprehensiveness and diversity of answers, as well as favorable comparisons to a global but graph-free approach using MapReduce source text summarization. For situations requiring many global queries over the same dataset, summaries of root-level communities in the entity-based graph index provide a data index that is both superior to NavRag and achieves competitive performance to other global methods at a fraction of the token cost. An open-source, Python-based implementation of both global and local GraphRag approaches is forthcoming at /aka.ms/GraphRag. This concludes the reading of From Local to Global, a GraphRag approach to query-focused summarization on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.